Welcome, and thank you for joining me. Today, I will be focusing on two important features of GemStone 2, using the Sensei Graph and the summary map. And this is Beth Hill speaking. We will be discussing how to set up the Sensei, the links between the Sensei and the summary map, and how these are used to explore normal, abnormal, and unknown events. Previous webinars have covered a general overview of GemStone and probability state modeling, building an analysis model, as well as cleanup strategies and using TRICOM to enumerate unknowns. For those of you new to GemStone, it is a comprehensive approach to high-dimensional flow analysis, incorporating a variety of features in one automatable program. The engine that runs GemStone is called probability state modeling. To the unfamiliar or for review, I refer you to this paper right here, as well as our YouTube channel where you can find previous webinars and videos. You can also check our website for publications. So as I mentioned, today I am going to focus on using GemStone's Sensei mapping and the summary map. Cen-se, which is an acronym for Gaussian Enhanced Nearest Neighbor Stochastic Embedding, is a dimensionality reduction algorithm that has been optimized for cytometry data. It is unique in that populations are identified and labeled automatically without having to use manual gating to determine the island identity. This map is interactive and high resolution, allowing you to see the structure inherent in the cell populations and delve deeper into subsets and subpopulations. The Sensei is linked to the model via the summary map, which provides the color coding and orientation of the cell types. The graph, however, is calculated independently of the model using all of the information in the sample file to account for each event. The Sensei is very flexible and versatile. A user can elect to focus it on all or just a few cell types, change graphics to suit preferences, and view the map in a frequency or heat map intensity mode. A user can draw a region around a population and animate the events, then look at the modeled cell types and then classified events to determine the phenotype and location of those events. This feature works both ways. Sensei is also very fast. You can try various approaches and will not be waiting forever to see your results. We'll be taking a closer look at these features as we progress. The algorithm has been published and the reference is shown here at the bottom right. So before adding sample files to the program, they should be compensated, unmixed, and normalized as appropriate. In develop mode, the transforms and scaling for the measurements should be optimized, as well as any editing using the measurement wizard. The first step in analysis is usually to clean up the data to remove debris and aggregates. If a separate model is used for a Sensei, this can help to confirm that unwanted events are removed. We use Sensei graphs during the model building process to help determine and confirm cell type and subset phenotypes, as well as to check for population overlap. The speed at which Sensei calculates helps to make this efficient and timely. And of course, a Sensei calculated with a completed model is used to compare sample files and visualize all populations. So right now I'm going to go to a live demo. And what you see in front of me, hopefully, is the GemStone workspace. And we have a report, just an empty report page. So a Sensei is actually set up on an empty report page. You can see this in front of me. I click here at the left toolbar, that little map icon. And then I'm going to draw a histogram, make it nice and big so you can see everything clearly. And you wait a minute and the Sensei plot will actually come up. I'm going to right click and say Edit Graphics. And this brings up a window where most of the controls for building and calculating the Sensei and the graphics are located. There are two tabs at the top left. One is a General and one is the Sensei tab. The General tab you can think of as sort of pre-calculation controls. The Sensei tab you can think of more as post-calculation controls. So what we would do when we're setting up a Sensei is we would come to the measurements and we would choose our measurements. And then this little choose measurements window appears. If you have a completed model, all of the measurements that are included in that model are actually already chosen for you. You can either deselect all and go in and just choose maybe iconic lineage measurements if you choose, or you can go back and select all. I've used a cleanup model previously, and you'll see these measurements come through here, but those are not selected, and we wouldn't want them to be present in our Sensei at this point. I'm going to click OK. Now, the other thing you might want to choose is the different cell types to be shown. So again, when you have a completed model, you'll see all the different cell types that are included in that model, which this is a PBMC sample. It's 33 color Aurora spectrophoto. And we have several different cell types modeled already, which are included. But again, you could deselect all and just choose a few. We'll demonstrate that in just a second, or select all. And let's say OK here. And then there's an option also to choose the maximum events to start calculating with, and some other things that we'll get into in just a minute. So I'll say OK, and then I'm going to come here. And if I hover over the Sensei, I'm going to get this toolbar here on the right. And I'm just going to say Build Sensei for all events. And it will immediately start calculating. You'll see, because this is a previous model, it's already been labeled, it's already been identified for populations, but you can really start seeing how things are resolving. There's a status bar here on the bottom left of the Sensei, which is telling you how much of it has been calculated. You can see how fast it's going, actually. And then on the bottom left of the GemStone workspace, you can also see that status bar as well. So if that is hidden, if this report page is hidden, you can see where we are in the process. And it's done. So the Sensei, there's a couple things that are really unique about the Sensei. And one, I'll just bring your attention down here to the bottom left. There's a key on the Sensei graph itself, and you'll see the number of events. So this is 189,697 events. So we started the calculation with 10,000 events and for speed. And then what Sensei does after we have the calculation is it goes back through the data file and assigns every one of those events to a position on the calculated Sensei. So it's looking at all of the information contained and then assigning it to where its nearest neighbor would be on the graph. So what you're looking at is really all of the events in the data file. This is important when you're looking at rare events or very abnormal events. You want to be sure you know that everything is accounted for. The other thing we can do here, because there are so many, I'm just going to come in here. I'm going to change, I'm not going to show all dots, I'm just going to change this to 50,000. It gives us a little bit clearer picture. So what you see here are the modeled populations. This population here at the top right are the T cells. You can see the different stages. This is color-coded. There, see the 8 T cells here. We have NKT and what we call mate cells. We have B cells here. There's gamma delta T cells, NK cells. We have basophil-like cells. That was my terminology. And then we have monos, we have classical, intermediate, and non-classical monos. So all of the cell types are represented. There are various things that you can do. I told you that this graph is interactive. We can actually zoom in on a population. If we come up here to the right, I'm going to just draw a region around the CD4 cells. So this zooms in on a cell type without recalculating the graph. And you can see all of the structure that's inherent in these CD4 T cells. You see the naive population here in red, and it sort of progresses down through central memory, effector memory, and then terminal effector. There's Tregs that are resolved here, and also some different various subpopulations within this effector and effector memory population. And then we can reset that zoom. We could also add a label if we wish. Just press that A. I'm going to just add a little text here. I'm going to say this are human PBMCs. Can make that a little bigger. And I'll say okay. So this, if you save this particular label, it will come up on all of your saved senseis. It's a great way for presentations and just to sort of label a graph. This will also, you can add keywords, you can add any kind of keyword that is in that data file. So that's a handy feature to have. You can draw an arrow to highlight a population. You can draw an ellipse to highlight a population. You can bring up the edit graphics window here, recalculate. And then we have these regions which are live regions. If I click on that polygon region, I'm just going to come here and draw a region here. And if I want to animate those, I just right-click on that region and I show region animation. You can see some blinking start to happen. I want to shut that off, and I'm going to just shut that off. And I'm going to come back to this, the animation, in just a few minutes. So we'll look at that a little bit more closely. The other thing I can do is I'm going to come back into my Edit Graphics box, and I'm going to come to my cell types, and I'm going to deselect all, and I'm just going to choose my CD4, CD8s, and this population here, and say OK. And then I'm going to say OK here, and I'm going to that, and I'm going to recalculate. So what I've done is I'm just going to show you the difference between how you would zoom in on a population and then recalculate just a couple cell types. And again, you can see the status bar. We're at about 33% now, and you can see these populations start to resolve. So the population on the left are the CD8 T cells. The population on the right are the CD4 T cells. And then it's going through, it's transferring all of the events that are just included in those cell types. And this is where you really start to see this structure that's sort of present and inherent in those cell types. We can see the Treg populations. There's a naive Treg population, which would be 127 low and 25 and CD25 positive. And then again, there's a effective memory Treg population. There's another little population down here that's 161 positive, and a little 56 positive, 57 positive effector. So you can really start to see those populations resolve, and any other named populations that you can see gives you a chance to actually start really delving into those populations. I'm going to come to a fully calculated Sensei that I've previously done with the same file. And I want to come back to my animation. Actually, I'm just going to come back here for 1 second. If I come back into my Edit Graphics window, I can rebuild this cell type list. And my cell type list is rebuilt to where it was previously. Say, okay, so let's come back to my Sensei. And I want to show you a little bit more about this unknown population. So I'm going to just draw an arrow, and this is the population that I'm interested in. It's not labeled. It's part of maybe the unclassified population or unassigned population, but it's similar to our MDCs, our PDCs, our monos over here in the bottom left. Going to draw a region around this. Come over to my region icon. Draw a nice region around that, and then right click and show my region animation. I'm going to come into my cell types and I'm going to open my other events. Now, if I open the first expression profile in this stack, these are all the measurements in the data file. I see these red blinking dots. This is going to show me the phenotype of that unknown population. So I have CD33 positive. If I highlight this, I can actually use my arrows or my page down and go through each one of those expression profiles to see the phenotypes. These are CD86 positive, or DIM, CD45 RA negative. They're CD14 DIM, and now it's sort of an interesting population that comes up over and over and over again that people don't necessarily seem to have a name for. Or agree on a name for anyway, and they're HLA-DR DIM, not completely negative, so this separates them from the monos and the rest. They're also 11C, sort of DIM, not brightly 11C positive, and so forth. I can look at all of the different populations here. The other thing I could do is go to my cell type, and you can see here that population, again, is CD14 DIM, but very closely related to the monos. Coming back to my Sensei, turn that off. The other way that this is interactive is I can come into my Edit Graphics again, and we're going to look at the Sensei tab. This is where I can change the color scheme of my graph. I can come here and I'm going to look at my intensity heat map. There's a drop-down menu where you can select all of your different measurements, and you can start at the top if you wish. Go to and just scroll through and see the expression of all of the measurements in your data file. So this is CCR7 that we're looking at right now. We can see that it's positive in both the naive CD4 T cells and naive CD8 T cells, and then we actually see how it downregulates as those T cells go through the maturation differentiation process. If I wanted to save that, I can right-click on this top white area. I can save this image, so I can save each one of those heat maps or just a particular heat map that we're more interested in, and then I can keep kind of going through and looking at that CD3, CD4, CD8, etc. I'm going to come back to my little drop-down menu. I'm going to come to my frequency heat map. So what you're looking at now are all of the populations in sort of a population density mode. You can see where the highest density of the events would be located. They pretty much follow all of our different cell types. The other thing we can do here is, if you wanted to change the background for that, we can change it to black, and that really pops that frequency mode. This makes a great publication and just a great presentation. Come back here. Change that back to white. Okay. And let's go back to our summary map colors. So we're back to where we started from. Now, where does this summary map fit in? If I come down here to the bottom where all of these tabs are on my workspace, I'm going to come to Maps, and here's the summary map. So this is calculated automatically during the batch processing of your data files. The batch is over here on the left. You read it in kind of a clockwise manner. So the inner nodes, there's CD8, CD4, NKTs, gamma delta T cells. The inner nodes represent the major cell types. And then connected to those are the subtypes or subsets of those major cell types. So we have the CD8, we have the center memory, effector memory, and so forth, and terminal effector. We have B cells, we have naive B cells, memory B cells. So you can, these are all to scale. They're all enumerated. If you hover over them, you can see the number of events and also the percentage of total events in the data file. The other important part of this is that you actually see this unclassified or unassigned population. So you know how many events are still unknowns, and you're able to delve a little bit further into those. I'll come back to my report. I can actually unhook that and bring it up next to my Sensei and kind of look back and forth, and I can see that my naive population of the CD4s is 11.228%, batching this over here. So this is to scale. All of the events are accounted for, and you can, and this is what provides the orientation of the cell types and also the color coding for the Sensei. So let me just bring your attention here just for a second to this population in my Sensei right here. I'm going to just draw an ellipse around here. So here are the CD4 terminal effector population. We have a couple of different subsets in here. I'm going to bring up another version of GemStone. This is the same model, using the same model, calculating another donor. And you can see this population that has sort of appeared. That clusters kind of close to those CD4 T cells, but not quite. It's still maybe part of that terminal effector population, but we have CD56 and CD57, kind of this expanded population. I'm going to grab my summary map, bring it up next to that, and I can actually see this terminal effector population of the CD4 T cells is greatly expanded, as well as this CD57 population and CD56 positive population in that subset as well. So this is one way that you actually end up looking at the unknowns. It's quite powerful, being able to compare different sample files in this way and actually have all of the events accounted for as well. So let me just come back to my presentation. I'm just going to bring this back up. Cut the slide and change these. Why they don't stay there. There we go. So looking at these two Sensei side by side, you can see that the cell type orientation is similar. We have the expanded population. It gives you a really good idea that maybe there's something unusual about this particular donor's PBMCs, or I don't know if we can call it abnormal, but it's at least a little unusual. And maybe there's some differences in these other populations as well. If you want, you can go through all of the different heat map intensities, looking at these different populations. You can see that this is CD3 positive. This expanded population is also CD4 positive, 56, partly 56 positive, partly 57 positive. So it's heterogeneous. And then PD1, quite a bit of it is PIM2 positive for PD1. And you could look through all of the different heat map intensities to see really if you can identify that population. The other way that this abnormal population may show up is just an expanded population that's part of the modeled cell type. So this is a recent paper. The reference is here for your perusal. And you can see on this CD14 by CD16 bivariate, we're looking at a monocytic population where this CD14 negative population is greatly expanded, which you can see down here on this Cen-se. So this would be a normal Cen-se for comparison. This is actually a Helios file, so it was calculated in Path Setter software, which is run by GemStone, available with the Helios data files. And then we have a population here that's a combined population of monos, PDCs, and MDCs, which is from a patient with a plasmacytoid dendritic cell neoplasm. So those are some of the ways that abnormalities will show up in your Cen-ses. You can also visualize your cleanup with a Cen-se. This is from a CyTOF file. On the left, you have an uncleaned or a file before the cleanup. I like to say unclean. But we have different populations. We have aggregates. We have debris. There's some beads. And then once it goes through the cleanup process and the file is exported from using GemStone and using a cleanup model, we can then see the cleaned events, which will go through for further analysis. This is after cleanup. And again, the same process occurs with the Aurora data before and after cleanup. So we can look at before cleanup, see a lot of different populations, and then after, the red events would be the events that will actually go through for further analysis. And we can look, if we wanted to, we could draw a little region around these gray populations and see if we can identify those, and they are like aggregates and debris and so forth. You can calculate a Cen-se without modeling any cell types. On the left is the same data file. It's just been calculated before any kind of modeling has been done. So the orientation is not quite the same because we don't have a summary map set up yet, but we do have the structure that is really recognizable. So the CD4 T cells are here, in comparison to these already modeled. You really do see a lot of the same structural features to each of these populations. It does also work with your intensity heat map. So if you want to calculate before you do any modeling, you can go through and identify the different populations. This is really helpful as you're going through the modeling process. So we have CD3, again, I mentioned those are the CD3 positive CD4 T cells, monos up here, very similar to the structures of the modeled populations. And then the abnormalities show up without modeling as well. So you can see this expanded population here. That would be that CD4 expanded terminal effector population. One of the interesting things that I've always found is that when we look at data file after data file after data file, depending on the donors, the similarities always just continue to astound me. So on the left, we're looking at a spectroflow. This is the 33 color Aurora file, and on the right, there's a Helios file. So the spectroflow, is calculated using the scatters. It's cleaned up using the scatters. The CyTOF obviously isn't, but we can really see the very great similarities. This is using a similar model, same donor, but we're seeing some real, definitely similarities between the populations. So that always makes me feel better when we get the same results with different programs and in different instruments. So, and this is, again, the same donor, so the numbers are very similar as well. So in summary, Cen-se is fast. I've shown you that it's pretty fast. It's interactive, it's consistent as far as cell type, orientation, and it's labeled automatically for you. You don't have to go through and do any manual gating. The Sensei has both frequency and intensity heat map modes, so you can really delve into your data file. The Sensei graphics can be customized for preferences and publications or communications, depending on what you need to do with it. And they're also saved automatically when you go through the batch process. It looks at all of the events in the data file. Every event is accounted for, and you can delve deeper into those unaccounted events. With the Sensei, we can zoom in on populations graphically or by calculation. A Sensei can be used to evaluate the cleanup, unmodeled files, or for the modeling process. Then no events are gated out. And this is really important. So that no unknown populations are lost. They're all visible and they're all accounted for. I showed you that CD14 dim population. And that it's really important when we start looking at rare and unknown events that we know exactly what we're looking at. So that's the end. I want to say thank you to SciTech for the Aurora data. Thank you to Fluidigm for the Helios data. Thank you for your attention and for joining us. If you have any questions, we do have some time. You can also email me. Here's our website.